In this video, I will be demonstrating how differentiation can be used in real-world applications. Let's start with a video of my friends playing catch with a baseball. As you can see, the baseball follows the path of a parabola. This means with some clever math tricks, we can use calculus and differentiation to find the instantaneous velocity of the ball at any time. For this demonstration, all you will need is something to film with and a brain. Let's get started. First, I flew my drone up into the air. This is completely unnecessary. An ordinary phone camera works just as well. Then I recorded a steady shot of my friends throwing a baseball. Let's replay this clip and plot some points to visualize the parabola. That's much better. Let's connect these points and draw an x and y axis so we can have a frame of reference. After this, we have to establish a scale. This is so that I can measure what's on screen and then accurately scale it to real life. I measured the on-screen height of my friend to be 2 1/8 inches. His actual height is 70 inches. In order to calculate the scale, all you have to do is divide his actual height by the on-screen measurement. Here, I calculated the scale to be 1 on-screen inch to 32.94 real-life inches. Now let's put the scale to the side and find the start point, end point, and vertex. We will be using the vertex to calculate the position graph of the baseball. Now that we actually know the vertex, we're going to plug this into the equation to find the graph of the parabola. But there's one extra step. We need to find the value of a. In this case, the easiest way to do this is using the origin, as this is just 0, 0. After we isolate for a, we can just plug in 0, 0 for y and x and find the value of a. Now that we use the vertex form to find the actual equation of the parabola, let's expand this into standard form. This will make it simpler for differentiation. This is where the fun begins. Using the power rule, you can find the derivative of the position graph. This will give you the velocity graph with respect to time. If you find the derivative of this graph again, it will give you the acceleration graph with respect to time. As we can see, the acceleration graph gives us a constant negative number. This means that the position graph is always concave down, which is true. It's a parabola. Now, using everything we just calculated, let's try and find the velocity at 2 seconds. Will the ball be speeding up, speeding down? Well, let's find out. After plugging in 2 to the velocity graph, we get 0.8099. But remember, there's a scale. In order to find the velocity in real life, let's multiply this number by 32.94. This gives us a final answer of 26.67 inches per second, or 2.2 feet per second. Now, if we want to calculate if the ball is speeding up or speeding down, let's write down our velocity at 2 seconds and our acceleration at 2 seconds. As you can see, at 2 seconds the velocity is positive and the acceleration is negative. This means that the ball is speeding down. If they were to be speeding up, the velocity and acceleration would be the same sign. We can fact check this by knowing how in real life, a ball will start with an initial velocity, hit a maximum height, and then fall back down. This is because on Earth, there's gravity, and the ball will keep on accelerating downwards. This is why we calculated the acceleration to be a negative value, meaning that the position graph is concave down, which is always true on Earth if you're throwing any projectile. To conclude this video, we demonstrated how projectiles move using calculus. Until the next project, I'll see you next time.